Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this transient thermal analysis using aster. I have taken this case from Sengel book. Here you can see I have specified Sengel heat transfer 2nd edition. In our case, we have taken a long 20 centimeter diameter cylindrical shaft made up of stainless steel 304. Comes out of an oven at a uniform temperature of 600 degrees Celsius. The shaft is then allowed to cool slowly in an environment chamber at 200 degrees Celsius with an average heat transfer coefficient of 80 watt per meter square degree Celsius. Determine the temperature at the center of the shaft 45 minutes after the start of the cooling process. Also determine the heat transfer per unit length of the shaft during this time period. So this is the case we are going to analyze. Here 20 centimeter diameter, long diameter cylindrical shaft they have mentioned. We can solve the problem by modeling a same diameter by specifying any unit length. Instead we can go for 2D also. To simplify the case, here I am going to solve the same case with a 2D case. Material property. Here they have specified stainless steel 304 at a room temperature. Thermal conductivity is 14.9 watt per meter degree Celsius. Density is 7900 kg per meter cube. And specific heat Cp is 477 joule per kg degree Celsius. And thermal diffusivity they have specified here. This is nothing but K by rho Cp. So we can derive this value from these three properties. For more accurate result can be obtained by using a property at average temperature. So in that book itself they have specified 360 degrees Celsius. The center of the shaft reaches 360 degrees Celsius in 45 minutes. If you don't know, we can specify we can solve it for 50 minutes or 1 hour. We can find in which minute it reaches 360 degrees Celsius. In that way we can solve it. In other way, as we know, this is reaches 45 degree. This is reached in 45 minutes. So we will solve it for 45 minutes and we'll check the result with aster. So now we'll go for software. I have kept my salome software here. Salome is the free and open source geometry and meshing software, and it has a solver called aster. So to open this, just open the terminal. This is the command to open this software. Now it's getting opened. Now we'll move into different models. First we'll go for geometry models to design our model. As I have mentioned previously, we can model same geometry by specifying unit length, because they have not specified the length of the shaft. By specifying unit length we can model this geometry and we can solve it in 3D case also. 3D case, it has bigger number of elements, nodes. It will take more time to solve. Instead we can go for 2D case, the same problem. We can get the accurate result and with the lesser time and lesser computation effort. So now I'm going to model the same geometry in SI unit. So this is, I'm going to convert into meter, divide by 100 I'm going to put it. So go to new entity, basic. There is an option called circle. Here we can go for center. So now we are going to solve it as a plane problem. In plane problem in aster we need to keep it in XY plane. So for that origin is 0 only. To draw our model Z, OZ we have to click it. Then only it will generate the sketch in XY plane. Now you can see it here. It's generating sketch in XY plane, the radius of 100. But in our case our radius is, they have specified diameter. Here I am putting the specified diameter is 0.2 meter. This is the diameter they have given. So we need to specify the radius here. Here you can see radius we need to specify, that is 0.1. Go to fit screen, you can see the circle, then you just give apply and close. Now we have created this circle. Now we need to build the face for this. Go to new entity, build face, just apply and close. Now we have generated our model. This is our model, we are going to solve it. Our ultimate aim is to find the temperature at center of the shaft after 45 minutes, at 45 minutes. So for that, what we can do, to find the node at the center, we can divide the surface by planes. Go to new entity, basic, there is an option called plane, center point, normal to x, make it the size of 1, apply. Similarly, center point, normal to y, same size 1, apply. Now we have created two planes. Now we can partition the plane by using this face. Before that, I am going to save this file. Go to pictures, code aster. This is my case, save it. Now I have saved it. So first you select the face one, go to operation, there is an option called partition. Tool object is these two planes, then just apply and close. Now you can see, now we divide this surface into 4 quarters. Why means then only we will get a node at the center, otherwise we will get a node at somewhere here, because the element will generate randomly. So now we will get node at the center. Now we can save this file. Now we will create a groups to apply the boundary conditions. As you can see here, it is cooling in the environment. There is a convection. Heat transfer coefficient is 80 and the external temperature is 200 degrees Celsius. This is the way we are going to do. So there is only one boundary condition, that is convection boundary condition. Just select this one. Go to new entity. There is an option called group, create group. Select this edge, select all the outer edges, press the shift and hold, select one by one, then you will get all the edges. Then just add it, it will add the edge number, and here you name it convection. Then you just apply it. There is, we can go for face also. We'll create all the faces into single group, just apply and close. Now we can save this file by pressing Ctrl and S. I have saved it. Then we have created the geometry and we have created the groups to apply the boundary condition. Now we can move into meshing model. Mesh. Now we are in mesh model. Select this partition 1. Go to mesh, create mesh. Here there are different algorithms are there. Now I am going to use NetGen 1D 2D algorithm. It will generate a triangular mesh. And here I am going to specify NetGen 2D simple parameter, local length, default it shows coarse mesh size 0.02 it shows. I am giving 0.05. Okay, and apply and close. Now we need to compute this mesh. Compute. Now we have generated a linear element of 2880 triangular elements and it has 1503 nodes. Now you can see here we got a node at the center of the shaft also. So now what we can do, we can go for solving. Before that, you just make sure you got your groups in your mesh, into your mesh. Now you just check your groups. So this is my edge group and this is my element group. Now we have done meshing. Now we can go into aster study to create the setup. So always choose table solver. Now we are in the aster study. Now we'll generate the command file or setup one by one. Right click, add a stage. Now we'll generate the stage one by one. First what we need to do, we need to read the mesh. Go to mesh. There is an option called read a mesh. So we can give any name. So I'm just giving default name. Here we can choose mesh 1. Now see, it is reading the mesh. Mesh format is MED. Just apply. See here, just layer mileage is the command. So just OK. Now we have read the mesh. Then what we want to do, we need to assign the finite element. What we need to say that what type of analysis we are going to solve. So assign to all. This is actually a thermic problem. This is a plane problem. So thermic plane. Just OK. Say apply. OK. Now we have specified the model. Now go to material. We need to define the material and we need to assign the material. So we need to say that to the software what type of material it is. So first we need to define the material. So any material, this is actually a steel 304 and there are different material models are there. This is actually thermal and isotropic heat conductive model. So the heat conductivity of this material is 14.9. So just go specify 14.9 and there is an option called volumetric heat capacity. Is nothing but density multiplication of specific heat. This is a record if you are doing transient analysis. If you are doing a steady state analysis, this property is not necessary. Only conductivity is enough. If you are doing transient analysis, we need to specify density as well as specific heat. This property is density multiplication of specific heat. So now we have density is 7900 and specific heat is 477. We need to multiply this value. But here we can give only integer, only number only we can give it. We cannot specify the formula. For that we can go for here variable. Just click it here. Here we can name it as row underscore cp. The value is, we can specify as a Python expression also. This is just a simple multiplication. 7900 into 477. So this is the value it will take. Just apply it. Just close it. Just OK. Now you see, just apply it. Now see, there is a variable which is generated at the initial stage. This is going to apply to the material. Just say OK. See, this row cp is a variable is generated and this row cp is applied to our command as a material. See, this is the material. This is the command for the material. So lambda is nothing but conductivity and row cp is row cp we have assigned. Now we have defined the material. We need to assign the material. Go to assign a material to the model. Everywhere. If you have 2 or 3 materials, we can go for assign to the group of element. Now we have only a single material. So everywhere is a simple way of assigning. Just apply it, say OK. Now we have assigned the material. Now then what we want to do, we need to specify the transient time steps. So as we have seen, in what time step it will reach, at 45 minutes, what is the temperature at the center of the shaft. So the time is 45 minutes. So here we need to take it as a second only because we are using SI unit. So now for that you just go to functions and list. There is an option called define list rel. So debut is nothing but initial value 0 to until means end value. So 45 into 60. Just go to calculator. 45 into 60. (2700 seconds) we need to calculate. And there is a step length. Every step how it has to be jumped. It has to be jumped by 1. So every time step it has to calculate up to 2700 seconds it has to calculate. So total number of time step is 2700. Just say OK. Just apply it. Say OK. And there is one more option is called as how it has to be calculated. There is an option called def list inst. Inst is nothing but time. Method, we need to choose auto. Auto is if it is not converging. If any one of the time step is getting diverged, means it will reduce the time step in its own and it will make to converge. That is to auto. Go for edit, time step list, just say OK, just apply it. Now we have specified the time period 0 to 2700. Now we'll go for boundary conditions. Just go here. There is an option called assign thermal load. Here initial temperature is 600 degrees Celsius. Then we are cooling into the environmental of 200 degrees Celsius external temperature and heat transfer coefficient is 80. This is the condition. So this is condition is exchange. It's nothing but convection group boundary condition. So group of element we can choose into edge group. This outside edge has to be convection, and by clicking this one it will activate this also, because this is we need two properties. One is heat transfer coefficient as well as external temperature. External temperature, see, external temperature is 200 and heat transfer coefficient is 80. Just specify it. Heat transfer coefficient is 80, external temperature is 200. Just say OK. Just apply it. Say OK. Now we have specified the boundary condition. There is no pre-analysis. Now we go for analysis. Here we want to do thermal analysis, linear thermal analysis. This is non-linear thermal analysis. There is no non-linear, only linear, but it is a transient. Loads, this is the load, say OK. Now we have defined the load, we have defined the model and material. Now there is an option called initial condition. If you are specifying initial condition in thermal analysis, it will become transient. If you are not specifying initial condition, it will become steady state. That is the way the solver is going to solve. I am specifying initial condition value of 600 as mentioned in the problem. It is 600. Initial temperature of this shaft is 600. Say OK. And time stepping, as we have defined the time step for list. So here list ER, so switch on this list ER. This is my time step 0 to 2000. These are need not to touch it, this will take automatically. Then I just say apply it, say OK. Now we have defined the analysis. Now we'll go for post processing. So anyway, the solver itself, it will calculate the primary variable of temperature. We'll keep this temperature. If you want to calculate flux, we can go for post processing, calc champ, thermic. So there is an option called flux LNO and flux node. Here it comes unnamed. Just give the name of rest, same name, whatever the name is there for solver, the same name you just give it. Just apply it, say OK. Now we'll go for saving the output file. There is an option called set output results. Choose the location where you want to save it. Here I'm just naming as result.rmed. This is the format for result file. Just save. Make this switch on. So mesh file, this has to be calc champ. Just save OK. Just apply it, save OK. There is an error it shows. Just have a look once. It's saving in the here itself. So just go Vengat. There is pictures, code aster. Here a file path contain unsupported symbols. You will not able to run code aster to continue. Yes. So there is unsupported symbol it shows. Just go to pictures, code aster. Yes, we have a space here, that's why it's not showing. So we need to remove the space. Now see, rename. Now we will save this file, save as. I'm just overwriting here, everything is saved there. Now we'll locate the file, then it will come. Go to pictures, code aster. Now there is no message come because the file doesn't have any space. Now format. Here we need to specify mesh file. Result file is a calcjam. We just choose into calcjam. Make it tut-36 as. Just save OK. Just apply and close. Now we have specified everything. So we'll check one by one. Mesh readed. So now we have done everything. Now we will save this file. We'll run the case. So first you just click this plus button. Just specify some more memory because it is a transient. It has to solve 2700 time sets. I'm specifying some more memory. Time period also I'm specifying so 50. It will not take that much time. Anyway, I'm just specifying this. Just make it into 5 seconds. Just run it. Just wait for a while. It will get solved and it will show the results. If any error comes, it will show the error message in the message file. So first see, it has started reading the command file and it started solving. Now it's going for up to the time step of 637. We can refresh. Now it is every time step it's converging and it's showing the results. It reaches 1356 this iteration. Now it is 2125th iteration. Now it is solved. It is done up to 2700 iterations. Now it's saving the results and now it's calculating the flux from the temperature. Now it's saving the results. If you want to see the file where it is running, we can see in the folder itself. Just go to the folder. This is my folder. So results file not it's saved here because it's calculating. Now see, it is came with a tick mark in green color, means it's saved result. It solved the case without any error. And now just go to the location. See, the result file is saved here, and just go to run case. So these are the file it is generated while solving. This is the message file, whatever we are seeing at the front. This is the message file, and this one is the command file. Whatever the setup we are creating as the command file, it will generate the command file. This is the mesh file. .mad is the mesh file. It's exporting and it taking for solving. This is the export file, whatever it's export file. These are the log files. Now we have done solving. Now we'll go for post processing to view the results. Just go into paraview. Now we are in the paraview post processor. Just go to open, home, just navigate into the folder. My result file is result.rmad. Just save OK. Just wait for a while. It is a little bigger file. We'll check the memory of the file. See, this is 488. So this is 488.1 MB. That's why it's taking time to read. Just apply it. So we have opened the result file. First what we need to do is we need to see it's showing 600 everywhere. What we need to do is we need to run the case initially. Just we need to run the case up to 2700 seconds. What it will do, it will read the result, complete results, and then it will the label will change and the legends also will change. Now the times are running. Now we'll see the case as we have mentioned in the problem. We have modeled and we have solved up to 45 minutes. Now we will check the results. What is the temperature at the center of the shaft? So as mentioned in the theoretical calculation, it is coming around 360 degrees Celsius. So now we will check with the result with the code aster. Now it is running with 1200. Now we'll see the code aster. So this is the website for code aster. Code aster is a structure and thermomechanical analysis for studies and research they have mentioned here. It has very good documentations and training materials for different and downloads. Here there is an option called salome. So this is the file I have installed. Just first download this file, then you just install the Singularity software. So you just install the Singularity software, then you just run this file. You will get open. You can run we can install code aster separately also. For that we need to install salome for separately. Now we'll check this. Now it is crossed 2300 degrees, 2300 time step. There are different way by viewing results are there. What surface with edges is nothing but it will show with the mesh. Surface means it will show only the surface. Now see, it has reached a 2700 iterations. Just change this in here and again change this into here. Now see, it's automatically changed the legends. Here also you can keep it. I'm just keeping here. So here I'm just changing this pattern into rainbow, blue to red, apply, close. Here there is option. Here we can make this into 12. Now I just change the legend into blue to red. Now we'll see how the temperature is running. So initially it is the temperature at 600 degrees Celsius. Now we are cooling it. How it is cooling in every seconds, we can watch it here. So from the external surface the temperature is getting reduced slowly. The outer surface only, first it will reduce, the temperature will get reduced, and then from that it will temperature will slowly to reduce from the inner core. Now we will go into surface with edge. So this is the way it will happen. I will go surface to watch it clearly. So here there is an option called different background. We can set it. White background we can set. Front background is the same white. Gray background, this is the gray background initially we have. This is gradient background like in abacus. Black background, you can set the black background also. So there are different background. This is the default background. So any background we can set it. I'm just keeping this gray background. Now around 450 degrees Celsius it reaches around 1196 seconds. Initially it is cooled very fast. Now you can see it is cooling very slowly because initially the temperature difference is very high. Now the temperature difference is small, that's why it's taking the temperature drop is very slow. The external surface reaches 330 degrees Celsius. You can see it here. But inner surface is not yet reached. Now it is reached 2700 seconds. That means 45 minutes. Now we'll check the temperature at the mid. Just go to surface with edge. So this is the mid node. We'll check what is the temperature at the mid node. Just go to the hover point to find the value at the mid node. It's taking that one. Now it is moving, it's not coming. What we can do, we can select this. Now just go for selection. Now just go to here. We'll set this here again. Let's go to over points. We need to place this point to the center point. edge, select the points, select the points through I don't know why it's selecting like this. So now we have selected these points. Now we'll check the results. Okay, point, now we have selected this point. Just go here, there is an option Windows Statistics Inspector, go to view, selection display inspector. Just switch on this selection display inspector. After, so now you can see selection display inspector, choose temperature. Now you can see the temperature value. So just moving this. So the mid node is this one. It reaches the temperature of, we can unselect actually. So this is the temperature, 364.09 is the temperature. It reaches around 2700. So instead of selecting all, we can go for selection of points, temperature. This one we can take. Yes. So 364.09 is the temperature at the mid center of the shaft. So this way we can calculate. Now we can plot this value also. Just unselect all, go to filter, search, plot, here there is option called plot over time. Just enter it. Now we need to select it, just apply it. Just wait for a while. Now it has generated the plot. Now just go to the plot at over time. So x-axis is the time. So total time is 0 to 2700. Now y-axis data is temperature. So just choose the temperature value in the node. So it's showing in different way. So this is showing an average value, actually maximum ticket. 364 is the value, maximum it's coming. So this is the value. This is the way we can plot the data also. So we can simulate this data also. Just simulate it. Now see in the particular node. So what is the temperature from initial to now? So initial temperature is 600. From 600 to it changes the value. Like that we can simulate it. In example, for this time, for 388 seconds the temperature reaches 588. Similarly we can simulate it. We can find the value at the center. So now we have completed. Now we can check the result with the analytical also. It's coming around 360. So around 4 degrees Celsius difference is showing. That is because of mesh and accuracy. We can change the mesh finer and finer, we can get the same results. Similarly, we can change the linear element to quadratic element, we can get the accurate results. So now we have completed the transient analysis of shaft using code aster. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.